Do you remember when I said that the purpose of machine learning is so that us humans can make better informed decisions? Think about how you make a decision. One method you might use is to think about them in a sequence of logic. For instance, say you have a job offer and are considering whether to accept the offer or let it go. When you think about the various factors involved in this decision, you will ask yourself questions in a series from the most important factor down to the least important. For example, is the salary good? Is probably your biggest factor. If yes, you ask again, is there an opportunity for growth? If yes, then will the company force me to relocate? If no, then do I like the people that interviewed me? And so on and so forth. After a series of questions, you'll end up with your final decision. And only if all of the paths you took to derive to your answer ends up in your favor, you will accept the job offer. This type of decision-making process happens every day in our lives, whether you think about it or not. The shape of all of the paths resemble a tree, and so this logical way of thinking is called a decision tree. More specifically, you made your decision through an algorithmic process called a decision tree. For every decision point, or a node, you've made branches that drove your decisions, and you finally end up at a leaf. This is the structure of a decision tree, and the decision tree can be thought of in data science and machine learning modeling perspective too. The decision tree algorithm is a method of non-parametric modeling, and that's what we'll discuss today. You may remember the XOR problem. If you need a review, you can go check out my video on it on the link in the screen. But to summarize what the XOR problem is, it's that the XOR logic isn't achievable with a linear separator, meaning that a linear line can't separate the pluses from the minuses or the ones from the zeros. To express the XOR logic, we had to bring in a very complex idea of a layered combination logic. Well, if you look closely, you can kind of see that this layered structure also resembles a tree structure, just put down sideways. Turns out, the decision tree can effectively express any logical combination of features, including the XOR. It might be easier to visualize this in decision boundaries. So let's say that we have x1 and x2. This data cannot be separated with a line. Instead, you'll want to draw something that looks like this curvature. But there's an easier way if you bring on a decision tree instead. Let's set up a tree logic like this. At the first node, we have x2 is less than 3, so we can separate with this line. On the left branch of this top node, we have x1 is less than 4, so this logic can separate this line beneath the line that separated the parent node. Same thing on the right side of the branch, we can separate this top section of the graph with this line, and the last logic, x2 is less than 5, with this line. Notice that each of the nodes can act as a linear separator. And now at the end, we have boundaries from a combination of linear lines where we can perfectly separate the ones and the zeros. Not only that, but each separated section is also either purely 1 or purely 0. Meaning that if we choose any section in this graph, we're 100% confident that all of the data points within that boundary is either all ones or all zeros. We're going to come back to this idea of purity in just a minute. But for now, the point of this exercise is that a decision tree can express all combinations of logic and create boundaries that allow you to partition the outcomes where each section is pure. So, understanding how the decision tree works and why it's useful, how do we exactly create and use these trees to learn from data? Let's go back to the job offer situation, and this time we'll make a small, real-looking data out of it. Here we have 3 factors: salary, growth, and relocation that is going to drive whether or not I'm going to accept the offer or not. For the decision tree, we'll have to decide what each node is going to be from the top of the tree all the way to each subsequent node. So how do we choose the splits? We're going to explore splitting strategies using 2 methods, one using entropy and another using the Gini coefficient. If you have a background in another scientific field, you might have heard of the term entropy. Entropy is a measure of uncertainty. In data science, entropy can be thought of as predictability based on the data. For example, let's just compare salary and accept columns. Without even looking at the data closely, you can imagine that job offers with great salaries are more likely to be accepted than those with worse salaries. Here we can say that if the job offer has a great salary, then we're less uncertain that the job is going to be accepted. Likewise, if the job offer has bad salary, we're less uncertain that the job is going to be rejected. So salary is a good indicator of acceptance, and therefore it has less uncertainty or less entropy. Approaching this in a more mathematical way, we need to calculate the entropy for each of the 3 variables. This can be done with the mathematical equation here. This quantifies the level of uncertainty of your feature variables against your label variable. So calculating only for salary, the entropy calculation takes the percent of the yeses times the log base 2 of the percent of the yeses minus the percent of the no's times the log base 2 of the percent of the no's for the great rows, and the equivalent for the good rows and the bad rows each. Now you compare that against its parent node. For this first split, the parent node is going to be the entropy using just the outcome variable from the entire dataset. Afterwards, you simply then take their subtraction, which is called information gain. In essence, information gain is literally a measure that tells you how much information can be gained going from the parent node to the child node. Intuitively, you want to split based on where the highest information gain is, so you want to make the most of your splits. So you can do the same thing with growth and relocation. Calculate all of the entropies and then calculate the information gain from the parent node. The feature variable with the highest information gain, or essentially the lowest entropy, is chosen to be the splitting variable. Following this logic, the tree gets split at every stage until each node can perfectly segment a decision. And so with this entropy and information gain logic, we can formulate this decision tree. Another method that we use is the Gini coefficient method. Conceptually, the Gini method and the entropy method is pretty much the same. The calculation is a bit simpler since it doesn't compute the log, but you're taking the sum of the percentages of each outcome labels squared and then taking the difference from 1. This measures impurity, which is slightly different from entropy. You can think of the squaring term as choosing the same outcome of a variable when chosen randomly. In a simpler example, imagine that you have a box with an unknown m number of red balls and an unknown n number of blue balls. If you're able to pick the same colored ball, say red, twice in a row, then you're more likely to believe that the box contains more red balls than blue balls. And assuming that's true, we can say that the box is more pure in the sense that it's plausible that it's made up of mostly one color. In a simplified way, this is what the Gini coefficient measures. So going back to our example, we can calculate the Gini coefficient for each of the variables again. I'm going to skip the details of the math this time, but you follow the same procedure as the entropy method, do the same with all of the variables, and then, just as we did with the entropy method, we can calculate the Gini reduction for each of those with the previous node. And the variable with the highest reduction gets chosen to be the splitter. With either method, you will end up with a decision tree that can be used to make a decision with your data. Now, you may notice one thing. If there is only one tree, you can imagine that every time you add a new data point with the same attributes, it's always going to predict just one outcome, which we know is almost never true in the real world. And if you build a new tree with a new example row, this can actually dramatically change the tree's structure, which we also don't want because modeling is all about consistency. The way we solve this problem is to turn a single tree into multiple trees that randomly vary from each other slightly. Enter random forest. Random forest builds multiple trees from the same data. There can be different strategies for how to build varying trees from the same data, but the most common method uses bootstrap sampling, which means random subsets of data from the training will be sampled, and feature bagging, which means that subsets of variables or features will be chosen. Each subset of data sampled using these two methods will be used to create its own tree. So we'll end up with several trees. And when it comes time to do a prediction on a new data, it'll run the new data on all of the different trees. The outcome of the trees are aggregated, and then the final prediction is typically made by majority vote in the case where the outcome variable is categorical, i.e. a classification task, or with an average where the outcome variable is numeric, i.e. a regression task. This idea of compiling individual algorithms and aggregating them is broadly termed as ensemble learning, and random forest is a classic example of it. Thankfully, as a data scientist, you won't have to do all of the calculations. That's what we use modeling packages like scikit-learn's random forest for. You will, however, need to decide a number of parameters depending on your data: the tree splitting function, the number of trees, max tree depth, and strategies for choosing data subsets are among the different hyperparameters you have to consider. Now, there is one type of ensemble learning method that came out of random forest, and that's called gradient boosting. To briefly explain, when a random forest is built, the number of trees are made at the same time in parallel. This is called bagging. Gradient boosting improves upon this idea by making each subsequent tree learn from the previous tree. It does this by calculating the error or the residual of the tree, and then train the next tree using that residual to minimize the error in the new tree. This can help the model learn faster and better, but it's more prone to overfitting. Anyway, whenever you come across an opportunity to do a random forest modeling, you should also try gradient boosting. The specific library you use is called XGBoost. So there you have decision trees and random forests in a nutshell. Random forest models get used very frequently in any data science role, so it's quite an essential thing to learn. If you would like to see a real-life example in a future video, leave a comment below to let me know.